In Chapter 11, we're going to start talking about hurricanes. This is the final chapter in our severe weather section of the course, but believe me, there are more severe weather events that we haven't been able to talk about in this course. We're going to start off in this video talking about the definition of a hurricane, as well as the formation and the anatomy of a hurricane. In the next video, we'll talk about the life and the movement of a hurricane, and in the final video, we'll be talking about naming a hurricane as well as forecasting for a hurricane. So hurricanes have lots of different names. The most common name that we are familiar with here in America is, of course, hurricane. But in the western North Pacific, in the area of Japan and Korea and China, they are more commonly known as a typhoon. Whereas if you look in Australia or India, it's more known as a cyclone or a tropical cyclone. There are a lot of different names for these storms, but they are all the same thing. And they are commonly known on the global scale as tropical cyclones. All right, so what do you need for a hurricane to form? You need the correct environment. Particularly, you need light wind, tropical waters with a temperature of 26.5 degrees Celsius or higher, as well as some sort of a trigger, and you need a little bit of Coriolis effect. I'm going to go through those a little bit more. You need light wind. If you have heavy wind, then it won't allow the storms to fully develop. It will take them and it'll because of wind shear, it will cause the storms to turn and torque and dissipate before they can develop into anything big. Tropical waters, you need tropical waters because they are going to be warm enough, 26.5 degrees Celsius or higher. And this will happen most often between the months of June and November. You need some sort of a trigger. You may have a lot of potential, a lot of energy. Things are ready to turn into a hurricane, but if you don't have something to kick it off, then it won't get going. Very often we see these as tropical waves, just low pressure systems that come off of the coast of Africa into the Atlantic Ocean. You also need the Coriolis effect. The hurricane has a spinning motion, as we all very well know, and in order to have that spinning motion, it has to have the Coriolis effect. But there is no Coriolis effect at all on the equator, so you can't have hurricanes on the equator. I will show you a figure in the next video that shows the paths of a hurricane, and you will very clearly see there are no storms recorded on the hurricane. So in the top part of this slide, you see all the right conditions for a hurricane, but even then, we still need the right conditions in other respects as well. For example, El Nino. For some reason, in El Nino years, you develop a strong subtropical jet, which will diminish the chance of a hurricane forming. Okay, so how does a hurricane form? First of all, the storm develops as just a simple cluster of thunderstorms, just a bunch of thunderstorms that start to rotate around a common low pressure. This is that trigger. We have a low pressure that comes off the coast of Africa, creates a bunch of thunderstorms. They start rotating around that low pressure. Then the winds around the warm water start to evaporate the water, and that warm water contains a lot of energy, and so that energy is put into all those storms. Well, all that energy rotating around the common low pressure, the water is going to condense and release latent heat into the core of that rotation. And since you're heating up the core, that's going to increase the pressure in the center, which causes the eye of the storm, which I'll show you in a bit. It also causes air at the top of the storm to diverge or move outwards in a clockwise fashion. Again, I'll show you that. And it's going to intensify the surface low, which is going to intensify the wind and the strength of the hurricane. So let me show you how this works. So you have air that starts to move around the low pressure in the center of the storm, which is going to evaporate a lot of warm water, which then starts to rise around the eye. And as it heats, or as it rises, it will start to condense, which dumps a lot of energy right here into the core, increases the temperature and thus increases the pressure right here in the center. And since it increases the pressure, it's going to cause sinking motion in the eye as well as in between each rain band. That's why you often have very clear skies on top of, or very clear skies in the middle of the eye of a hurricane. In addition to having descending air, this high pressure at the top also causes an outflow, a clockwise outflow around the top of a hurricane. And so there's the whole picture of a hurricane. So you end up getting some sort of a circulation pattern like this. You have a very intense low pressure, low here because it's lower pressure than anywhere else horizontally, with a high pressure on top of that, high because it's a higher pressure than anywhere around it. Okay, so pressure is low. So if you were to fly an airplane right along the surface, what you would see is that the air pressure would drop and drop and drop, and you'd have the sharpest drop in temperature right near the eye. And you'd hit that low, and that pressure, of course, is as low as it'll get. And then right after that, your pressure suddenly starts to increase and then tapers off, gets back to normal air pressure. Well, remember from chapter 6 when we talked about wind, what causes wind? Pressure gradients or changes in pressure. So here, your pressure is changing, but the pressure is changing over a large distance, so you're not going to have very fast winds here. But here in the eye wall, right next to the core of the storm, your pressure is changing at a much faster rate. Since your pressure is changing at a faster rate, this is where your strongest winds are going to be. So you have lightest winds out in the outer skirts, strongest winds at the eye wall. Then right in the center of the eye, there is no change in pressure at all, so you get no winds in the eye. Now, how can you weaken or dissipate a storm? Well, you need the right conditions, either strong winds, like you have a low pressure system or a jet stream, or some other sort of wind currents, wind system, or you need cooler waters, or even no waters. The strong winds will break up the rotation of the storm, and thus keep it from developing and becoming a really fast rotating storm. And the cool waters, of course, take out the energy of a storm. Now, we need to point out here that we still have a lot to learn about hurricanes. We've still only scratched the surface about these hurricanes, so there are constantly studies being done on hurricanes. So we've kind of touched on these already. These are the four main parts of a hurricane. You have the eye wall, the rain band, and the cap, which is the anticyclonic divergence. And of course, you can see them all. The eye is the very center where there's a high pressure with sinking air. The eye wall, which is just around the eye where you have the most intense winds. And then you have the spiral rain bands that come all the way around. Then you have the anticyclonic divergence. You can't see it very well in this picture, but I will show you in just a second. Here's the eye of Hurricane Ivan from 2004. What's really cool, if you can't see it, but if you were able to, if you looked up at a really high detailed image, you would actually be able to see the ocean down there in the center of the eye. Obviously, this is being taken from the International Space Station. And so it's pretty impressive to see the water from space. Here's the eye wall in the middle of Hurricane Katrina in 2005. So you can see a very strong eye wall around the sides, clear blue skies in the eye. Now here's the impressive thing. This down here looks like a bunch of clouds. Over here you may have some, but this is primarily ocean waves. These are ocean waves from the hurricane. So that's how clear the skies are in an eye. Rain bands, very strong areas of intense wind and rainfall. This is Hurricane Ike from 2008. And of course, this is where you get the most intense rain. Here's a three-dimensional radar image. Pretty cool that we can do this now. Pretty awesome technology. And then here is an interesting picture of Hurricane Luis from 1995. Obviously, you can see the rain bands coming in counterclockwise into the low, but you can see kind of here's a good spot right here. You can see a clockwise rotation going out. This is the anticyclonic divergence, the cap of a hurricane.